Hi, my name is Ard Westerveld, and I'd like to tell you about the cool things we do involving robotics in an unstructured agricultural environment. With we, I mean the Smart Mechatronics and Robotics Research Group of Saxion University of Applied Sciences. We currently have a team of about 45 researchers, and we run approximately 30 projects simultaneously each year. We are located in Enschede, in the east of the Netherlands, close to the German border. Together with public organizations, small and medium enterprises, and other knowledge institutes, we've been focusing on making an impact to society for the last 10 years. This has resulted in a lot of publicity in newspapers and professional scientific journals, and besides that, we aim to share our knowledge of robotics, mechatronics, and artificial intelligence with the community during conferences and workshops. We have many application areas for our projects involving mechatronic systems, industrial robots, ground robots, and drones. Here you see some short examples from past projects we did. For example, in the bottom left, a gas leak detection system to autonomously navigate gas pipes and check for potential leaks. The application domain I'd like to focus on today is precision agriculture. Within this domain, we have several projects ongoing. For example, automated fruit picking and automated detection of white flies in Gerbera flower greenhouses. For now, I'd like to highlight a project we did recently regarding the removal of weeds close to crops. In this project, the focus was on automating weed removal very close to crops, as those weeds are the challenge in sustainable weed management. For an automated weed removal system, many different aspects are important. However, to scope our project, we initially focused on the weed removal action and left the detection and navigation out of scope. However, we had integration with detection and navigation systems in mind from the very beginning of the project. As there are many different sorts of weeds, probably there won't be a single tool to target them all. Therefore, we took a modular approach by decoupling the tool for plant interaction from the positioning module. In addition, we defined interfaces to a crop and weed detection module to be able to later integrate our solution with existing robots. During the project, we compared several possible tool solutions and did tests with scorching the weed with heat in our lab. Touching the weeds for about half a second at 300 degrees Celsius did result in the weed disappearing after a few days. In greenhouse tests, we used an even higher temperature and also proved the tool to be effective in removing smaller weeds. Therefore, this approach was selected as our initial tool. We developed a custom-built 4-degree freedom tool positioner, initially for the scorching tool, but we kept in mind that different tools might be needed for different types of weed. Although the vision detection part was left out of scope, we did some initial tests in our lab for detecting plant features with a YOLO V7 network in order to be able to target the most vulnerable part of the weed with our scorching tool. In this video, you see some initial results showing successful classification and location estimation of both crops and weeds. We controlled the tool positioning module with ROS2 and modeled the crops as conical no-go zones to plant paths to the weeds without harming the crops. Here you see initial lab tests of our positioning algorithm in a static situation. Eventually, we would like to attack the weeds while moving, so we need compensation of the vehicle's movement. But we would still like to use planning algorithms that are tried and tested in the industry. To achieve that, we added dynamic motion compensation to the static planning algorithm. With that, we were able to stay on the weeds while moving over the field. Therefore, our positioning module has a larger range of motion in the driving direction. This allows for statically planning motions from weed to weed and then adding vehicle motion compensation to move the entire planning frame over the workspace, as is explained in the animation on the left, where the total workspace is shown by the green rectangle in the camera's field of view is in front of the system, and the planning frame, which is continuously compensating for the vehicle motion, is shown by the dashed square. In the video on the right, you see the results of our lab tests with this dynamic positioning scenario. To test our solution in the field, we used pre-measured crop and weed locations and evaluated whether the system was able to plan movements from weed to weed without damaging the crops. In this video, you see the results of those tests. As I mentioned in the beginning, we kept integration with detection and navigation systems in mind from the very beginning of the project, and because of that, we were successful in integrating the developed tool relatively easy with the robot developed by Pixel Farming Robotics, which was one of the partners in this project. In this video, you see the integration result, where the detection system from the robot was used together with our system to target specific positions for a certain amount of time while the robot keeps moving. So, in conclusion, we developed an effective tool for weed removal, which proved a good solution, especially for smaller weeds. We were able to integrate that in a positioning module, which also allows for compensation of vehicle motion. Because we kept modularity in mind from the very beginning, we could easily integrate the solution with an existing robot. For future research, we plan to further look into the recognition of relevant plant features, as better understanding of the environment can improve the planning and control of the required actions. Also, we aim to further generalize the concept into modular building blocks with standardized interfaces and make both hardware and software open source available in a way that end users can use the solution in their daily agricultural practice. Thanks to you for listening, and also thanks to our partners in contributing to this research project. In case you have any questions, feel free to ask or reach out later.